Now we're going to develop the Euler turbomachinery equations. So starting with our torque formula that we ended with in the last lecture, we can calculate the power, the water horsepower here. The water horsepower we know is equal to omega times the torque. That's back from thermodynamics. You remember the energy imparted by application of torque. So you have that, and so we just multiply this formula by omega to get our water horsepower calculation. So that's our first uh, actual result. We can calculate water horsepower if we know VT out, VT in, and these various parameters like volumetric flow rate and density, of course, and angular velocity of the pump shaft. We can continue with that analysis to say if water horsepower is equal to, well, omega R2, we already said that was the tip velocity. Remember, U2 was equal to the tip velocity of the outer tip of the blade is omega R2, and the tip velocity of the in part of the blade is omega R1. So those are our tip velocities. So we could calculate the water horsepower in terms of rho and Q dot, and then call this U2 VT out minus U1 VT in. So that's another way of looking at that. We also showed before that the water horsepower was equal to rho G H Q dot. So this was back when we were looking at the initially looking at turbomachinery. So that's the water horsepower can be related to, basically it's a change in potential energy. I mean, the H is your net head. So that's the effectively as if you had raised the water to this height in meters times your rho g. That's going to be your, your mass times your gravitational acceleration times your height times your volumetric flow rate is going to give you your water horsepower to basically move that water upstream. We showed that before. But if we take this and we solve it for H, we get H equals the water horsepower over rho g and then the volumetric flow rate. And now we can take this equation, plug it in here for our water horsepower. So we have our H there, and we say that's equal to rho Q dot times U2 VT out minus U1 VT in, and we put that over rho G and Q dot. Well, the Q dots, of course, cancel, the rho's cancel. So we end up with a pretty clean expression for the net head prediction as well. So the net head can be predicted as being U2 VT out minus U1 VT in divided by G. So there's another one of Euler's turbomachinery equations. So we have this one. We have this one is actually considered one of them. This net head is equal to the water horsepower divided by rho G Q dot. And we have this one, which allows us to calculate the water horsepower. So this one, and this one, which you can't see, are our Euler's turbomachinery equations. So we can predict water horsepower and net head based on tip velocities and things of that nature. When we're doing the idealized evaluation of the fluid, we assume that the velocity enters perpendicular to the impeller surface. So for the ideal analysis, we assume fluid enters perpendicular to the impeller surface. I'll say the impeller region surface. So it doesn't come in with any velocity that isn't normal to the surface. So here's our surface. Here's our blade coming along with some angle beta 1. So that's our blade angle. This is going to be traveling, of course, with our U1 velocity, which we said is equal to the omega times R1. Of course, here's our R1 here. R1, here's our circle. There's R1. So the blade is whipping along, and as we said, what's going to happen is this fluid that comes in, it's suddenly going to be, imparted, with a velocity due to the blade, and that's going to shove the fluid upward as it has to ride up this blade. So we're going to draw that picture here. So the fluid is flying along, it's sitting there minding its own business. The blade comes whipping along at speed U1, and that's going to drive the fluid up the blade. So this is your angle beta. So the blade, the bottom of the blade has moved here. So if you imagine a piece of fluid that started here, this, blade is going to come under, and it's going to push the fluid upward by that amount as the blade comes under it. So this is going to end up being your normal velocity. So you can calculate that normal velocity based on this geometric argument if you assume that this is perpendicular, and that's what we're assuming. So we're assuming that the velocity imparted to the fluid is entirely normal, but the blade speed is going to come whipping under it. That's going to drive the fluid directly upward. And so when you do that, that means that this is going to be your Vn, and you know this speed because that depends on your angular velocity and your R1. So that's usually what you can control. You can control how fast you turn the shaft. You can control what the radius of that position of your blade is, and you can control the angle of the blade, this beta 1 angle. So that's going to allow you to calculate how fast fluid comes into your pump. And so that's going to be true. That's going to allow us to complete our analysis and get us to actually be able to make predictions of things like flow rates based on those velocities and things. So if you look at this diagram again, you can see that the normal velocity, that inlet velocity over U1, the blade speed, is going to equal the tangent of beta 1. So the tangent of beta 1 is equal to V sub n at the inlet divided by U1. So we can solve for Vn at the inlet, and it's just equal to U1 times the tangent of beta 1. So this is going to turn out to be really important because we know that U1 is equal to omega R1. So those are design parameters that are under our control. Beta 1 is under our control. That means we can now create the normal inlet velocity that we want by selecting omega R1 and beta 1 in our pump design. Once we have this, we can use all those other relationships we developed to figure out head, water horsepower, etc. So this is going to this allows us to predict Q dot, H, and water horsepower based on the design parameters. So we've got these equations, and then we're going to have our Euler turbomachinery equations to get us to be able to predict all of this stuff.